gradual decline and and disappearance of the adult muscle presence from this introduction scenario. So prevention strategy. You might say that even though these muscles are going to disappear after about 5 years, maybe it wouldn't be worth it to start chlorinating the water. But as I said earlier, the Hudson River experienced a very significant decline in phytoplankton levels in only 2 years, so it's significant in that matter. And the economic damage that these muscles are going to cause along that certain stretch that will populate heavily during those 5 years will end up justifying a chlorination plan. So what I have in mind is a continuous level of chlorination plan of about 0.5 parts per million along small segments of the Susquehanna to try to minimize the collateral damage. And how I implemented this plan into my differential equation, I took the mortality term here and I added another term, C, which denotes the chemical concentration or the mortification effects of that concentration at a given location x during a given UT and a given day tau. So right now I've only implemented it in a rather simple way, and I've assumed that we could be able to keep the concentration more or less constant over the stream over which it is implemented, and is implemented at every year equally. Now, if I were to increase sophistication, I might have a dispersion model as it is swept downstream with the developers, but at this point, that's all I've got. And it's a pretty reasonable simplification, I would say. So then I looked at different scales of implementation. I looked at a 20-kilometer stretch, a 50-kilometer stretch, and a 100-kilometer stretch. So then you can see the progressively greater reductions in invasion severity as we chlorinate this beginning part of the stream during the settling period. So while the invasion will proceed to reach a max density of about 2,000 muscles per square meter, here it's slightly reduced with this small scale implementation, even greater reduction here, and an even greater reduction with the 100-kilometer implementation. So here's kind of a summary. You have a very significant decrease in the max muscle density with this increase in scope of the prevention plan that I proposed. So the recommendation is to use this continuous low level chlorination plan because the particular aspects of this plan in that we would only have to implement it for about 7 to 28 days over such a small span of the river, maximum 100 kilometers. That would minimize the collateral damage while maximizing the benefits in terms of reduction in ecological and economical costs downstream. And I guess I already touched on that. Extensions. My model is pretty flexible in that I would only need to go back into that same GIS file and extract data describing a different river system, and I would need some data describing the zebra mussel density growth or zebra mussel population growth in a similar water system to that other system I'm studying to make an exact or to replicate the study in another system. So I could look at any other system in the world with the appropriate data. And also I could, with the same basic general framework, you can look at, you can model the spread of a different invasive species entirely. Because the same kind of dual dynamics in terms of immobile adults that are sending out these velgers, larvae, juveniles, what have you, that then become adults later on. Those are seen in other plants, other marine organisms, and land organisms as well. So you can use the same computational techniques with a slightly different model structure in that way. And I would like to acknowledge my awesome mentor, Duke Ryder, because he's pretty much the best. Yeah. And that's it.